Morning. I'm Fred Chong. I'm from the University of Chicago. I'm going to do something a little different now, I think. We're going to talk about quantum computation. And what we're going to do is I'm going to spend 30 minutes giving you sort of an overview of why we're here today, why is this interesting, what are the interesting research issues that we're dealing with, especially what can software and applications do. And then we're actually going to do a hands-on demo. This is actually we're going to do an excerpt from a half-day tutorial that we do on tools and research in quantum computing. And so my two students here, Ryan and Pranav, are going to hand out USB sticks. And there's an installation on there that you can do. While I'm talking, and most of the demo will be after the break, so this will give you time to sort of get it installed and get it running. And we'll talk more about that. Pranav is going to start talking after I talk, and they'll give you a sort of a short demo, a quantum chemistry demo, actually. Okay, so what am I going to talk about today? I'm going to talk about where we are in quantum computation, and in particular, where we have a project called EPIC, which is what's called an NSF expedition in computing. And the project is basically looking at how can we connect algorithms to realistic machines of today and the next 5 years. And how can we do that in a way that greatly increases the efficiency of those algorithms running on those machines. And the way we're going to do that is we have this fairly fun team of computer scientists and algorithms people and physicists, which is this EPIC team. Okay, is this on? All right, there we go. So just a quick slide. You're going to get these USB keys, and there's a Docker image on there. And so you're going to, the instructions are on there. You're going to load the Docker image. If you don't have a laptop, you can pair up with someone. And if you don't want to install it on your laptop, you can pair up with someone. Well, we've done this before, usually in teams of 2. This is a sort of it's a Jupyter Notebook-based system. It has R software and IBM's what's called their QuizKit software. So this toolchain actually allows you to go directly from an application written in a sort of C-like language down to the IBM machines. Now, unfortunately, today we don't have priority access to the IBM machines, so we're going to just run on simulators. But when you go home, you can sign up for an IBM token, and then you can run your code on a real machine. Okay? And then I think that's all we need for today. Oh, the other thing I'll say is the software that you're getting in the Docker installation was for our half-day tutorial. So you can ignore the part about the token to run on a real machine, which we're not going to do today. Okay? And more on that later. All right, so let's get to the technical part of this. Why look at quantum computation, right? We're actually at a very exciting time for quantum computation. And why has this been something of interest for the last 15 or 20 years? Quantum computation is interesting because it's the only technology that we know that can sort of fundamentally change what we think is computable. It's the only technology with which every device that we add can potentially increase the power of computation exponentially, right? And that potential exponential power could allow us to solve currently intractable problems, such as things in chemistry, simulation, and optimization, especially in the near future. And of course, that's interesting because that could lead to better materials, photovoltaics. Even Microsoft has a formulation for the Haber process to look at better nitrogen fixation. Right? So there are a lot of sort of interesting grand challenge things here, and there's a big effort in building quantum machines because of this and because of sort of crypto security implications. We're also at an interesting time because Moore's law, particularly Dennard scaling, is slowing down. So quantum technology gives us a chance to, for key applications or very specific things, perhaps give us a different way to scale computation. And finally, there's sort of been a healthy competition between quantum computing and classical computing over the years. And even if our quantum algorithms don't immediately yield sort of superior results, it has led to insights in chemistry, physics, and cryptography. And sort of the best way, so we're currently focusing on quantum chemistry. One of the best ways to get better classical quantum algorithms is to have better classical chemistry algorithms is to have quantum algorithms that seem very competitive or perhaps better. Right? So I mentioned that we're sort of at an exciting time. We're at a time where for the first time we have machines that are of non-trivial size. Right? These are very exciting machines because 2 to the 50 or if we had a machine that really had 2 to the 100 states from 100 quantum bits, if those were perfect quantum bits, we would definitely be computing some really interesting things. Unfortunately, they're not perfect quantum bits. They're noisy and not reliable. And John Preskill at Caltech, who has been sort of a long-time figure in quantum computation, has coined this sort of interesting term called NISQ, which is a noisy intermediate scale quantum computer. And we're really, as he says, at a privileged time in history because we're going to have machines which can run algorithms that we've never been able to run before, right? So we can't simulate machines certainly of 2 to the 100 quantum bits, right? And so we're going to be looking at a lot of algorithms that, in fact, we don't quite understand their behavior theoretically, and we can't understand it empirically, so we're definitely going to have new science very soon. And we hope to actually be able to compute things that can't be computed on the largest classical machines. Now, even though we're at this extremely exciting time, the algorithms that we're familiar with traditionally require many more resources, many more quantum bits than the machines that we can expect in the next 5 to 10 years, right? And so if we look at the evolution of quantum machines, they're increasing exponentially, although very early in their development. Yet the algorithms that we're most familiar with, for example, Shor's algorithm to factor the product of 2 large primes, require many, many quantum bits. Grover's algorithm, which is a search or actually sort of function inversion algorithm, takes even more bits to really be profitable, right? And so we have this huge gap in terms of the machines that we have or expect to have in the near future and the algorithms that we want to run. Now, in the last, say, 5 years, we have an explosion of algorithms that are nearer term. Okay? Now, these algorithms are very interesting because they have practical applications. So that's quantum simulation, quantum chemistry, something called quantum approximate optimization algorithm that allows us to do things like graph optimization. However, these algorithms are actually, they're heuristic. We don't know whether they have, what their computational advantage is. And so we really need to run these on real machines and actually see how they react to the noise of those real machines. Even with these algorithms, however, we see that there's still going to be a bit of a gap between the machines that we expect and how many quantum bits we need. And so the effort that we have in our project and in a number of other companies and research groups is to build a software stack that allows us to adapt the algorithms to the physical machines and also potentially adapt the physical machine devices to the algorithms. And that's really, it's a pretty traditional stack of algorithms to programming languages, to compilers, to an architecture model, modeling of the devices, noise models, and then development of the devices. And we have this fairly aggressive goal, which we think actually is attainable, is with this kind of sort of full stack optimization, which really hasn't been done before in this area, we can increase the efficiency of algorithms on these machines by 2 to 3 orders of magnitude. And the reason why that's interesting is that 2 to 3 orders of magnitude translates to about 10 to 20 years of development in terms of machines getting bigger, right? So that's the goal. One subtlety that I'd like to mention is that when you look at the sort of development of quantum machines in the press. For example, you get an announcement from Google or IBM that says, we have a 50-qubit machine or a 72-qubit machine. That focuses on the number of quantum bits, which is a very simple metric from a sort of public point of view, right? But actually, the real figure of merit is both the number of quantum bits and the number of instructions or gates, logical gates that we can do on each machine. And we can think of that as a volume of sort of number of bits times the amount of computation, right? And the reason why that's interesting is because the reliability of an instruction, or what we call a logical gate, is actually the limiting factor right now in machines. So they can build a machine with a lot of bits, but they can't do too many operations on them before they fail, right? So if that gate error is 10 to the minus 3, for example, that means you can only do 1,000 operations, right? So if you have one quantum bit, then you can do 1,000 operations on it. If you have 1,000 quantum bits, you can only do one operation on each one before the machine fails, right? And you can sort of balance that, 32 bits, 32 operations each. So you can see that even though you can build a big machine, you get into this problem that you can't do much with it, right? So if you look at what Google is saying, right, they hope to have a machine in the next 5 years, which is about 100 quantum bits, where you can run about 1,000 operations on each one. And that means that you have to have a 10 to the minus 5 reliability for every gate. Now, this is very different from classical computing. These reliability numbers are so terrible that you're just at the limit of doing any small computation before the machine fails, right? Now, this actually is very interesting because 128 quantum bits is a lot. And that's 2 to the 128 states, right? And 1,000 operations is enough to maybe do some quantum chemistry or some sort of interesting computation. So this is a nice target for us. So the reason I bring this up is because when we look at software optimizations and writing applications for these machines, we're going to try to minimize both the number of quantum bits we use and the number of instructions or gates that we use, right? And so, or we might trade the two off and try to minimize the product. So this is something that the IBM calls the quantum volume, right? So it's basically a space-time volume. Okay. So this is, I think, a good thing to talk about here. I'm often asked, what makes a good quantum application, right? If you are an application scientist or you have different science that you want to do, what is likely to be something that you can run on a quantum computer, right? So these are sort of, at least right now, or for the foreseeable future, the constraints that we expect for a quantum machine. The first thing is that quantum machines basically have an I/O problem, right? You don't have very many bits to start with, tens, 100 bits. You can only get so much in there. Actually, there's an exponential amount of state in there, right? But typically, what you want to do is you want to put in a small number of bits that represent a problem that then requires an exponential amount of computation, right? So small, compact problems for input are something that we want to do. So for example, a function, for example, factorizing the product of two primes. That's easy to represent, very hard to do. Putting in small molecules that you're trying to model for chemistry, putting in small graphs that are then you do an optimization that might be difficult to do, that's exponentially difficult. These are the kinds of problems that we know how to do right now. You want a high complexity computation, right? So you want to take that, for example, your 1024-bit RSA key, you want to factor that. It takes a lot of computation, right? And we have an algorithm to do that. And then we need a compact solution, because the way quantum machines work is then you measure the quantum bits, and they actually collapse into a single classical value, right? So if you have 100 quantum bits, you measure it, you're going to get a 100-bit classical number out of that, right? So then the answer has to be very compact. For example, in factorization, that's easy because you get a factor, you try to see if it's the correct factor, right? For quantum chemistry, you're getting different energy states. Now, that gets back to this other issue, which is the machines are typically not reliable. They can easily have errors. The algorithms actually commonly have probabilistic elements in them. So for example, in Shor's algorithm, you have to choose a coprime to the thing you're trying to factor. And the coprime is hard to choose, so you choose a random number. and then you run the algorithm, and then if the algorithm doesn't come up with a factor, you choose another random number for the coprime, right? So there's a random aspect to it. So all of these algorithms are essentially probabilistic in some sense. You run them multiple times. You'll see on the IBM machines, because of the noise in the machine, they basically run 100 or 1,000 trials, and they take a histogram of the answer. Then you need an easily verifiable solution. So for Shor's algorithm, that's easy because you're taking two numbers, you're multiplying together. Is that the thing that you try to factor, right? For quantum chemistry, it's a little more subtle. You're getting an energy value. You need to compare that with the best classical simulations or best experimental values and sort of use your judgment, right? Now, one thing that's sort of nice that's developed in the last few years is this idea of co-processing between classical supercomputers and quantum machines. You think of the quantum machine as an accelerator, a hardware accelerator. And this is very nice for quantum chemistry. So there's something called a variational quantum eigensolver, which is actually part of the demo that you'll be doing today. And the idea is you take the best known solution from classical models on a supercomputer. You take that solution and you use that to seed the quantum algorithm. And the quantum algorithm will do essentially a kind of search and look for a better solution. And then you hand that back to the classical algorithm, and then you go back and forth and hope that the two work together to get you a better solution. Now, this is very nice because from the quantum computing perspective, quantum computing is a disruptive developing technology. As we've seen many times in the past with such technologies, as they develop, you're very hopeful, but the classical technology keeps developing too. And you may never beat the classical technology on its own terms, right? In this case, we're leveraging both. And so improvements in classical machines and algorithms also improve the baseline that we start from for the quantum machine. And so the idea is we could imagine improving quantum chemistry this way, even with both things improving. And finally, the problem that we've had for quite some time is that there are maybe half a dozen quantum algorithms, like true quantum algorithms, that are good. And so you only, your application has to fit into some part of it has to be accelerated by those algorithms. There's something like about 100 variations of those algorithms, but in the end, your application has to fit into essentially a lot of them are sort of energy minimization kinds of things, either for graphs or molecules. And then a few have sort of algebraic properties such as factorization, right? But when you go to sort of try to code up an algorithm to exploit quantum computation, these are the aspects, the things that you have to consider. Now, you might imagine that from an application point of view, there might be, because there's so few kernels, there might be sort of a library-based approach of coding up applications. And Google has actually just come up with a software package to do that, which I haven't played with yet, but it's mostly focused on quantum chemistry. But there are some tools that are already trying to exploit the sort of this constrained nature of what you're trying to do. OK. So I'm going to talk a little bit about our software stack in terms of thinking of it in terms of a compiler that compiles from a high-level program to circuits, essentially, right? And this is a very similar problem to circuit synthesis, if any of you are familiar with that, where you're basically taking a high-level program and going all the way down to a chip. It's a little bit similar to that, more similar to circuit synthesis than, say, compilation for general-purpose machines, because you typically know most of the program inputs in the control flow at compile time, right? So it's a very constrained problem, not a lot of branching, not a lot of dynamic behavior. And it's a constrained enough problem that we are willing to compile for, say, many hours on a specific instance of a specific problem. Let's say that we want to do factorization of a 1024-bit key. We would compile for exactly that problem. We would even compile for exactly the key, right? Because that's a problem that might take years on a classical machine and might take hours on a quantum machine. But we might spend hours or days even compiling it first, right? Now, having the programs known at compile time is interesting because it immediately causes resources to explode when you're using in your compiler, because you can do a sort of an infinite amount of loop unrolling and constant propagation. All the optimizations that you're used to, which are limited by how dynamic the program is, are no longer limited by that. They're just limited by how much memory you have for your compiler. We have very scarce resources, right? So we have very few qubits, very few instructions or gates. We're basically back to the 1950s in classical computing, right? Which is actually quite fun if you're a researcher, because, I don't know, as an architect, I always think, if only I was alive in the 50s, it'd been so easy to come up with lots of cool ideas. Well, this is in the 50s, basically. And then we also have an issue that it's a little bit like approximate computation, where everything we have to manage errors and precision. Okay, so this is our tool flow, which you can get on GitHub, and actually you're going to get in the Docker distribution. But the Docker distribution makes it transparent to run it. If you actually want to use this tool flow or play with it, you'd want to get the actual GitHub installation. It is sort of a standard LLVM compiler infrastructure, and it uses just multiple passes to do all the optimizations that are actually pretty similar to traditional optimizations, most of them. And then there's an architectural simulator that looks at different quantum computing technologies and architectures. And this tool set we used for maybe about 10 years. But what's interesting is over the last 10 years, we've been focusing on the problem at the request of government agencies, really, of compiling for really large quantum computers that don't exist yet. 100,000, a million quantum bits, okay? Right now, we're sort of pivoting, as we speak, to the near-term machines that are, say, 100 quantum bits, okay? So let me just start with, for those machines that are really large, we looked at a number of different quantum algorithms, and we were able to use all these transformations and sort of compilation steps to optimize for parallelism, okay, and improve performance. And these are some of our early results where we did that, where basically these bars are showing that for each application, we expose more and more parallelism through things like loop unrolling, constant propagation, mapping, and scheduling, all the things you're sort of used to in supercomputing, right? But where we are now is we're going to go to a period where we have to break the abstractions that we're used to and optimize for small machines, okay? And that means worrying less about scalability and also worrying less about clean abstractions between the layers of software. Okay? So I'm going to give you a couple examples of such things, which are going to lead to those sort of factors of 10, 2, 5, or 10, which we hope will compose to factor of 100 or 1,000 to give us better efficiency, right? Okay, so this is an interesting, so we start at the microarchitecture level. This is not our work, but this is a paper from Delft University, where what they've done is they've built a microarchitecture to control a quantum chip. And the most interesting thing about this is it's sort of a pretty traditional microprogrammed machine, except that in that sort of yellow area, what it does is it queues up all the instructions into these asynchronous queues, and it plays them back at gigahertz speed. So basically, you're turning the program, the digital program that you're used to, into a series of real-time analog controls. They're basically microwave pulses to control the physical machine. So the most interesting thing about this architecture is that it manages this real-time aspect of quantum computing, because, for example, you can't have a big pause in your quantum computation because there's something called decoherence that happens as you wait. And also, you need to just constantly keep these control pulses going to keep the machine in a sort of a known good state. Okay, so this is sort of an interesting paper. Now, what's interesting about it from my perspective is it defines an instruction set, right? An ISA, which basically looks like, x86 or whatever you're used to, but it's quantum gates, okay? Now, that's nice. They built this. It really works. But I would argue that it's maybe too early to define an instruction set for a quantum machine. And in fact, we may want to skip directly from software to control pulses without instructions, okay? And I'm going to show you one reason why. So this is some work that we've done recently. So on the left of this, where it says gate-based, that's traditional instructions, so 2-bit instructions, right? So which is a logical gate. As I go to the right, what I'm doing is I'm taking those instructions, collapsing them into a bigger instruction, essentially. So a 3-bit, 5-bit, 10-bit instruction. Only goes to 5-bit in this result. And I'm thinking of it as a transformation from a start state to an end state for 5 qubits, okay? And then what I do is I essentially do gradient descent classically to figure out what control pulses to get me from this place to this other place. And it's an exponentially scaling problem, okay? So we can only maybe get to 10 bits so far. So what's interesting is if you do that, I mean, what it is that the 2-qubit gates on the left, which are our instructions that we use in our traditional machine, aren't actually so necessarily that easy to implement on the real machine, okay? So it's not that the instructions that we chose are that well matched to the real machine. Instead, if we have complete freedom to choose what pulses to do, we can actually be very efficient. In fact, what this does is this is number of control pulses, which is basically proportional to time. And what you see here is going from the left to the right, on the blue line, we get about a factor of 2. So we get a factor of 2, basically, factor of 2 faster, because it uses fewer control pulses to get to the same place, as if we had done it with traditional instructions. So what we do with traditional instructions is we get a 2-qubit instruction, we turn it into pulses, and we just turn each one into pulses. So here we just figure out, well, glom them all together and get something very efficient. We can get probably a factor of 10 out of this, actually, which is good in our factor of 100 that we want. And what does this say? This is for this algorithm called QAOA, which is essentially like a sort of simulated, it's an energy minimization problem that you can use on graphs, okay, or other optimization problems. So this is sort of a neat way to get up to a factor of 10, but it totally breaks layers of software, right? Basically, I'm just going to skip a whole bunch of layers in our tool chain. And that's what I think we're going to have to do, at least in the near term. Here's another thing that we have to do all the time. We have to map data, right? This is a very typical problem in classical supercomputing, in implementing chips, right? Mapping to ASICs. We have to take a graph of computation and we have to map it. And we do this all the time. And it's interesting because in the quantum case, everything is very static, so we can do things statically. But it's also the case that even though we know that things are statically, there's a trade-off between the global view of the graph as, like I take a function, I think of it as a graph. I can map it really well. But the function, actually during the function, things sort of change. And you can think of it is that there's sort of right now 2 extremes. The static way of taking a graph and putting it into a graph partitioner, and the greedy way of just adapting to the computation as it goes, right? So in a lot of the machine vendors, Intel, for example, has a greedy scheduler and mapper because they have a very irregular architecture and a very small program, and it ends up maybe working better, right? So we have some trade-off between these 2 things. And then, let's see, I cut out that part. Okay, so let me just, I'm just giving you a really quick overview because I want to leave some time for the demo. One of the other big problems that we have is we're in this sort of ridiculous bootstrapping mode where we have programs, we have software that we can't run, right? And when we run them, we're going to be running them on machines that probably have a lot of problems, right? Because we're just pushing the edge of technology. So this is the perfect situation for some sort of formal methods to prove that the software and the applications have some form of correctness. Because we want to know when we run it on the machine, is it the software or the machine that's causing the error, right? And so we're in this very interesting time right now. And this is actually a very fundamental question because it turns out one way to test a program is to simulate it. And one way to verify, a lot of verification techniques are essentially simulating the computation of the program, or maybe of similar complexity. So the real question is, so if we talk about quantum simulation, when I talk to my MIT theory colleagues, they're really interested in this problem because from their perspective, if we come up with a good way to simulate an algorithm that's efficient and say scales polynomially, we've basically proven that that algorithm is no good. Right? The algorithm does not have an exponential advantage. So from their perspective, they work both sides of the problem, right? They want to try to disprove that something is exponentially difficult to do by simulating it. For what I'm interested in more probably is, can we verify computations that we think are exponentially difficult, right? And can we come up with some sort of verification property that isn't completely simulating the computation, right? So and thus doesn't run afoul of this, theoretical constraint that you shouldn't be able to simulate it, right? But maybe you can come up with some different kinds of properties that can teach you something about whether that program is correct, or at least identify different kinds of bugs. Now, it's very difficult for us to actually tailor this so far because there aren't that many quantum programs. We're hoping to maybe study how people write quantum programs with IBM because they have a lot of users, for example. So this is an interesting part of our project that we're working on. And in the end, where we really are is we have different abstractions that exist in these different layers. And they're good as a starting point. But in the end, I think we're really at a place where we need to break those abstractions and figure out, maybe this stack doesn't look so much like what we think it should look like, right? Or at least traditionally. And then I talked about this gap between algorithms and devices. We actually have this other interesting gap, at least in our research and our perspective, which is we did a lot of work on the right where we looked at giant machines. We're going to do a lot of work in the next 5 years looking at very near-term, noisy, small machines. The question is, what's going to happen in the middle as we evolve, right? And actually, for classical machines, we started on the left and we got to the right. We got to the point we stopped worrying about bits, how many bits we use so much. We stopped worrying about errors so much, although that's coming back, right? But I think with quantum machines, we're probably always going to be somewhere in the middle. And a lot of the things we learn on the left in terms of how to deal with specific sort of errors and noise are going to probably persist into the future. Okay, so I don't have it here, but I think maybe Pranav has it in his slides. There's a website called EPIC, which you can look up, and that has the full tutorial, videos of Peter Shor talking about QAOA, all kinds of, and some of us talking. And so now Pranav is going to do an excerpt from that tutorial.